Let's understand how we solved this numerical. The molar conductivities of KCl, NaCl and KNO3 are 152, 128 and 111 second per centimeter per mole respectively. What is the molar conductivity of NaNO3? And these are the options. Alright, so let's see how do we do it. Let's try and understand a bit of basic. Now, this symbol is for molar conductivity of electrolyte. This symbol is for molar conductivity of electrolyte at infinite dilution or zero concentration. We know zero concentration. Why are we calling it as zero concentration? Because when you dilute, suppose I have taken 1 molar solution, I keep on diluting it. So obviously the molarity will keep on reducing, and at a particular level it would become nearly negligible. The concentration would get negligible, and that is what we call it as infinite dilution. Okay. Now for strong electrolyte, Kohlrausch had set up an equation where molar conductivity of electrolyte was equal to molar conductivity of electrolyte at infinite dilution minus A root C, where C was concentration. Now if we observe this equation, this is very close to Y is equal to mx plus C. Only thing is here it is negative m. Y, so Y is what? Y is molar conductivity, so that obviously would be the y-axis, molar conductivity, whereas x-axis would be root of concentration, x-axis. So as we keep on coming over here, the concentration keeps on decreasing and it comes to infinite dilution over here. Alright, so now this equation was for strong electrolytes. So this dotted line which I have represented over here, that belongs to strong electrolyte. So what happens is, as the dilution increases, the concentration keeps on decreasing. So even if we have 2 points, we can plot a line, and on extrapolation, alright, so we can get molar conductivity of electrolyte at infinite dilution or zero concentration just by extrapolating this line. So there was no problem with strong electrolyte in finding this. We call it as lambda cap 0. Alright, so this is molar conductivity at infinite dilution or zero concentration. Alright, so no problem. Thus, lambda cap 0 can be found out by extrapolation of line obtained by graph of molar conductivity of electrolyte versus root of concentration. Fine, so no problem. But we had problem when we tried to find lambda cap 0 for weak electrolyte, because weak in case of as soon as we diluted or the concentration was reduced, we found that there was some relationship at initial level, but after that what happened there, with further dilution the line became parallel to y-axis, so it became difficult for us to determine lambda cap 0 for weak electrolytes. So just read it. But was not true for weak electrolyte. This was for strong electrolyte, but this was not true. This was not true for weak electrolyte. For weak, Kohlrausch generated law of independent migration of ions. Law of independent migration of ions. Okay, now let's understand what it is. In case of law of independent migration of ions, as per law, both cations and anions contribute to molar conductivity of electrolyte at zero concentration. Alright, so see. So this is infinite dilution, molar conductivity at infinite dilution. So that would be equal to independent molar conductivities of cations and anions. Now for example, if we have barium hydroxide, now at infinite dilution, the contribution would be from molar conductivity of barium and also contribution of molar conductivity of hydroxides, 2 of hydroxides, because we have got 2. So this theory is very significant for calculating molar conductivity at infinite dilution of weak electrolytes from those of strong electrolytes. How? Now let us take our example and try and understand. This method can be used for finding lambda cap 0, that is a molar conductivity of electrolyte, of weak electrolyte at infinite dilution, knowing values of HCl, NaCl and sodium acetate. Now see, mind you, these are all, we can find out molar conductivity of these electrolytes as they are all strong, and this is also a salt. So just see how we can do it. So what we do is we write the equation for molar conductivity at infinite dilution for acetic acid, which is equal to, for HCl, for sodium acetate minus that of sodium chloride. So what happens? This dissociates into molar conductivity of individual ions. Alright, and then what we can see is we can cancel this molar conductivity with this molar conductivity, this molar conductivity with this molar conductivity, and what we are left with is molar conductivity of acetate ion and that of H ion, H plus ion. Alright, so this is how Kohlrausch method helps us in determining molar conductivity of electrolyte at infinite dilution for weak electrolytes. Now the example that we have chosen for CET is not for weak electrolytes, but it is using the same technology and finding out the molar conductivity of electrolyte at infinite dilution for unknown salt. The molar conductivity of NaNO3 is to be found out from molar conductivities of KCl, NaCl and KNO3 using Kohlrausch methodology. So we have got to find, in our case here, in this numerical that I have chosen, we have got to find out molar conductivity of NaNO3 using molar conductivities of KCl, NaCl, KNO3 which are provided. And for this we are going to use Kohlrausch methodology. How? Just let's check it out. Now in this example, basically it is all about salts. Alright, so this is KCl, so infinite dilution of KCl is provided, so we can write it this way. Alright, we can write it in terms of molar conductivity of ions. Then again, in case of sodium chloride, the value is provided, we can dissociate it this way. Alright, that is molar conductivity of ions of Na plus and Cl minus contributing towards this. Similarly, KNO3 also, ions of potassium and nitrate providing the molar conductivity independent of each other. Alright, so now what do? We are interested in finding NaNO3. So we took infinite dilution for NaCl plus infinite dilution of KNO3 minus infinite dilution of KCl. Now why did we do? Dissociated. Alright, dissociated contribution. Alright, as they contribute. Now this I did negative. Now why? Now check this out. Now since this is there, this gets cancelled with this gets cancelled with this. So what I am left with is molar conductivity of Na plus molar conductivity of NO3 minus. So that itself is infinite molar conductivity. That itself is molar conductivity at infinite dilution of NaNO3. Alright, so what do? We substitute the values, respective values over there, and when we find out, we end up with this value. So answer is B.